Hello, welcome one and all. Today we are tackling the animal transport problem on HackerRank. This is a hard problem. My name is Glitch Failure. I'm a data engineer by day and a learner by night. I like to do coding challenges, capture the flag stuff, and some fun projects also. So if you're here for that, welcome. This one is definitely a doozy, and I will be going into great detail on how to solve this problem, and I'll even have a little bonus at the end on how to boost some efficiency out of the performance, because I have struggled with this problem for about 2 years now. In hindsight, it was really a problem of Python, the language specifically. It is a very slow language, and I was bumping into issues getting the test to pass simply because I was using Python. I was determined to use just Python, not C, not any other language that's lower level. This is me, Glitch Failure. I was able to get a working solution for this, but it took basically everything in me to do that, and I thought I would provide the solution and explain it because this is essentially the help that I did not get. I will go into again a lot of detail. Let's get into it. All right, animal transport. Capetta is working part-time for an animal shipping company. He needs to pick up animals from various zoos and drop them to other zoos. The company ships 4 kinds of animals: elephants, dogs, cats, and mice. There are M zoos numbered 1 through M. So keep in mind, this is 1 base indexing. Also, there are N animals. And for each animal, Capetta knows its type, such as elephant, dog, cat, or mouse, the source zoo where it gets picked up, as well as the destination zoo where it needs to be delivered. Capetta is given a truck with a huge capacity where N animals can easily fit. He is also given additional instructions. He must visit the zoos in increasing order. He cannot skip zoos. Dogs are scared of elephants. Cats are scared of dogs. Obviously can't be on the same train. Mice are scared of cats, and elephants are scared of mice. Also, loading and unloading animals are complicated, or is complicated. So once an animal is loaded onto a truck, that animal will only be unloaded at its destination. Because of these reasons, Capetta might not be able to transport all of the animals. He will need to ignore some animals. Which ones? The company decided to leave that decision for Capetta. He is asked to prepare a report and present it at a board meeting of the company. Capetta needs to report that a minimum number of zoos that must be reached so that she or he is able to transport X animals for each X from 1 to N. What they're essentially saying is that you need to return a list where the first element refers to how early can one animal be delivered, and you put the zoo number for that. Again, 1 base indexing. Also, you return -1 if it's impossible to transport an animal. So you can imagine at the tail end of the list, you'll have a lot of -1s because that's where you may not be able to transport any more animals at that point. Okay, so here is an example they give with a specific output, and this is sort of what it's talking about, where the -1s kind of show up at the end. For this first example, which is this test right here, this is referring to 10 zoos and 3 animals. The answer would be 5, 8, -1 apparently. This means that the soonest you can deliver 1 animal is at zoo number 5. The soonest you can deliver 2 animals is at zoo 8, and there is no solution for 3 animals. Okay, so I'm going to let you give you some time to do it on your own, and we'll come back with my solution. All right, good luck. There are essentially 2 ways of tackling this. One is with I want to put quotes here, the naive solution. I put quotes because the naive solution is using dynamic programming, which in my head is never naive. I will not go into that today. If you're interested in the dynamic programming approach, I actually do have that solution kind of explained over here. Dynamic programming approach will only pass about 30% of the test because this thing balloons out very quickly. We're told that the number of zoos and number of animals can be potentially 10 to the 5th power. Those are some pretty large numbers. How can we be better, do better? The idea is that we should probably use something called a segmentation tree. I actually, a previous video somewhere I'll put over here probably of my video on explaining how a segmentation tree works and how it can be implemented. What we'll be using is a segmentation tree for this solution. It is really great at working with aggregates over a range, and that's exactly what we'll be working with. I will explain one other thing about this problem. So this is unnecessarily complicated, which is another gripe. I think at the end I'm going to have a whole little rant, but this is one thing. This whole setup with the dogs, cats, mice, and elephants, you can actually pair the cats with the elephants safely, and the dogs and the mice work safely together. Just keeping that in mind. We're basically still dealing with 2 different trucks, and that's it. A cat truck and a dog truck. So that I will be saying right off the bat. Another minor thing is some of these are going to include a source zoo that happens after the destination zoo. We can't go backwards. We have to go in an increasing order, we're told. So here, yeah, we must visit the zoos in increasing order, and so we have to filter those out. What are we using the segmentation tree for? We're able to ask very quickly and efficiently, what is the maximum number of animals that could be delivered between zoo 1 and zoo 9 or any number of... Okay, so let's say that we have these animals on the left here. Consider these to be unsorted, right? There's just no rhyme or reason to them. And what we need to do is create another list. I'm going to call this the source zoos by destination list. And so we have 20 zoos. I have my cats and my dogs. And I'm basically creating two lists of lists. The first one being the cats, the next one being the dogs. This number represents the destination. So we can see here that at zoo 5, there is one dog that is dropped off. That dog was sourced from zoo 3. We see here at zoo 8, there was a dog dropped off here that was started or picked up at zoo 7. At the last zoo, zoo 20, there were two animals, two cats. It's not in order, right? It's 16 before the 1, right? I'm going to showcase why that doesn't matter. All right, and here is how our algorithm is essentially going to work. For each animal type, the dog and the cats, we're going to keep them separate. We're going to compile all those animals into this list that I'm talking about, the source zoos by destination list. That'll take big O of N. Again, this is counting source, so it's doing that in fairly quick time. We're not sorting the animals in the typical n log n way. Then we're going to create a custom segmentation tree for each animal type. Then all we need to do is iterate through each zoo. So the first zoo is 1, 2, 3. We're going to go like that. Now, if there are any animals delivered at that current zoo from this list that we're talking about, so you can imagine we go 1, there's nothing, 2, nothing, all the way up to 5. Oh, there's an animal. Then we can stop and do something there. So if there are any animals being delivered at the current zoo, then we're going to go to our segmentation tree and add 1 to all previously processed animals within that range between 1 and whatever that source zoo is. So in this case, for this zoo 5, we would stop because we see an animal being delivered. We would tell the dog segmentation tree to increment by 1 all values between 1 and 3. Then we ask both segmentation trees, hey, what is the maximum number of animals that could be delivered up to this point? And that will give us two numbers, and we basically take the max between those two, the one for the cats, the one for the dogs, and we will store that in our intermediate answer list, which is the zoo max counts list. This is a list that is one value for each zoo, which is the number of animals that could be delivered. We're going to convert that to the answer later. What's important is after we get that max value, we actually want to pass that information back to the segmentation trees to make sure that they are updated and are aware of the best max so far. That way they can make more optimized decisions. I'll say this right off the bat. This whole algorithm I just mentioned is not intuitive in any way. Okay, so we're going to go through this very slowly. Get pen and paper out if you need to figure this stuff out. Just for the moment, we're going to be treating the segmentation tree as a black box. We will not get into implementation until a little bit later. This is our source zoos by destination zoo list. I'm using currently this table as my test. You can pause this and kind of look at it, maybe write this down if you need to. We are starting at 1, so we're iterating 1 zoo at a time. There's not much going on until zoo number 5, so let's just kind of skip ahead and get to zoo 5 because that's when stuff actually starts happening. We have one animal, a dog, that would be delivered, and it started out at zoo number 3. So right away we need to tell our segmentation tree, hey, add 1 to that range between 1 and 3. Right now, the dog one is the one being updated. We're basically saying add 1 to that range between 1, 2, and 3. Now, I will note here that this is not exactly what's happening in our segmentation tree because we're going to implement it in a very different way. I'm trying to help visualize this in a way that is easy to understand. So even though you see this list here, this is not how it's actually going to look when we actually implement it, okay? And then we go here and we can say, okay, now that everything's updated, we can ask what is the maximum number of animals that could be delivered between zoo number 1 and zoo number 5, the current zoo. The cat is going to say 0 because it hasn't done anything yet, and the dogs will say 1 because that is the max value within the whole segmentation tree at that point. And so we're going to take that max and we're going to add it to our zoo max counts list. Then, and this is kind of the magic, we're going to now take that information, the max of 1, and we're going to update our segmentation trees with it. We're going to go back here. We don't need to update the dog because the dog segmentation tree already knows what the max is. We're going to go to zoo number 5 and we're going to say, hey, the max is 1 now. So now the cat tree is aware if you were to pick up a cat after this point, after you've already delivered this one dog, then the truck is empty, and therefore you can pick up a cat. And that's the kind of like optimization we're talking about here. There's not much going on here until zoo 8. We have one animal, a dog, that would be delivered, and it started out at zoo 5. So again, we're gonna just kind of go through the process again of telling the dog segmentation tree between 1 and 7, just add 1 to it. We get to ask both trees, hey, what is the maximum number of animals between 1 and 8, the current zoo? We get 1 from the cats, and we get 2 from the dogs. We take the max, 2. We go to our zoo max counts list, go to 8, because that's the current zoo, and we say 2 is the max. Then we take that information, we go to the cat segmentation tree, we go to 8 and say 2 is the best so far, just to keep it up to date. You see that at zoo 12, we get 1 animal, a cat, that would be picked up from source zoo number 10. So we're gonna have to tell the cat segmentation tree between 1 and 10, we add 1 to everything. And so now this animal, which would have been picked up at zoo 10, is now essentially being added to the previous processed dogs. And we can see that at number 8 here. So we have a max here that reflects 3 animals being delivered. We don't really specify which ones because we don't really care. We just want the count. For the first time, we're seeing the benefit of like having this setup where we're able to optimize. We're asking what's the maximum value between 1 and 12, the current zoo. We get 3 for the cats and 2 for the dogs. We take 3 as the max, pop that into our zoo max counts list at zoo number 12, and then we update the segmentation trees, but this time we don't need to update the cat because it knows about 3. We tell the dog, hey, at zoo 12, max was 3. Zoo 14, we do the same thing. The cat gets updated. It got picked up at zoo 13. We then ask the max. It's now 4 to 3. 4 is now the max. So we go to 14 on our list, say 4, update the segmentation trees. This time the dog needs to be updated. So 14 is 4 there. We go to one more. We go to 15. 15 has an animal that was picked up at zoo 2. This is kind of interesting because if this animal is being picked up at zoo number 2, then there really isn't a whole lot of space for it to optimize because the dogs were picked up and delivered somewhere in between there. And that's what we see here when we do the update. We're going to update by adding 1 between 1 and 2, essentially. We see that there's still a 4 max here. What you do see here, though, which is kind of cool, is that you see the number 3. And that number represents how many cats would be delivered if you just basically had a truck of all cats, which is 1, 2, and 3, these 3. We ask what's the max, we get 4 and 4. And here's kind of what's interesting. Because they're both the same value, well, we still fill in 4 for number 15 here, the current zoo. But what do we do with the update? Both of those segmentation trees, they have 4 as the max. They don't need to be told that anymore. So we don't need to update them at all when they agree on the max. On zoo 17, we have a cat picked up at 4, so we need to update between 1 and 4. We add 1 across that. We ask what's the max. Again, we get a 4. At zoo 17, we get a 4 here. Again, for the update, we don't need to do anything because they both understand that 4 is the max. We have at zoo 18, 2 dogs being dropped off. They were picked up at zoo 11 and 6. Notice that the order here is kind of out of order. So how does that make sense? So what we're doing is essentially the same thing. And we're adding 1 between the range between 1 and 6. And then we're adding 1 again between the range of 1 and 11. Here we have a max of 4, so that's not really changing. What's the max between 1 and 18? The current zoo, we have 4. We put at zoo 18 4, and we don't need to update these trees. They're very well aware of 4 being the max. We have a cat who was picked up at 9. We increment between 1 and 9. So this 5, you'll notice here, the 1 and 2, that basically represents a truck of all cats. At 8, if you can remember, 8 actually represented 1 dog being picked up from a while ago, but we kept incrementing by 1 by 1 by 1. So this is essentially this universe where 1 dog was picked up, then 4 cats were picked up afterwards. We have a 5 either way, but that's, I think, kind of interesting to think about what these numbers actually represent in the list. We ask what's the max. We see 5 from the cats, 4 from the dogs. We of course take the 5, and we now say at zoo 19 we get 5 animals as the max. We definitely want to update the dog to make sure it's aware. At number 19, we say 5 is the max for you. And at the end, we get 2 animals, 16 and 1 sources for the cats, and we need to increment those. And we see actually 7 is the max for this. You can imagine, again, what that represents. That means that you just have a truck of all cats. We take 7 as the max and implement that in our list here. So at 20, we have 7. So we tell our dog segmentation tree, hey, at zoo 20, we have a max of 7. So now we're done actually processing all the max counts for each zoo. We're gonna have to convert this into our answer list. Here is our zoo max counts list again. What's the earliest we can deliver 1 animal? At zoo number 5. What's the earliest for 2 animals? 8. 3 is 12. 4 is 14. 5 is actually 19. And you'll notice that the 4, we see 4 is all the way across here, but the earliest one was 14. That's why we say 14 there. And for 5, it's 19. For 6, it's 20, which will count for both 6 and 7. After that, we have no values for 8, 9, 10, 11, or 12. So we have a bunch of negative ones at the end of our answer. So far, we've been treating the segmentation tree like a black box. First, you might not even know what a segmentation tree is. I'll just quickly go into what that is. It's just a data structure that allows you to query and update a list for aggregation. Okay, so for example, a list that is 1, 4, 6, 2, and you want to know the sum of the range between 1 inclusive and 4 exclusive. The segmentation tree basically does that operation in log n time. Not only do you query quickly, you can also update quickly. How can it do these operations quickly? It's basically doing pre-calculation. Whenever you do an update, you pre-calculate and you bubble up the new values, update the parents so that they are aware of it. When you query again, now you don't need to go as far. You don't need to go like to search the entire tree. If we want to represent our list 1, 4, 6, 2 as a segmentation tree, the bottom here, which is those 4 values, 1, 4, 6, 2. You'll notice here that this node here, because it has these 2 children's, when you're doing a sum aggregation, then the parent here is the aggregation of those 2, 1 and 4. So that parent, which represents the range between 0 and 1, and again, when I say that range, I'm talking about like the original list index between 0 and 1. That's 1 and 4 equals 5. Number 3 in the segmentation tree has 8 because it represents the range between 2 and 3, and that's 6 plus 2, right? And then the root represents the entire list between index 0 and 3, and that is basically the aggregation of the entire list. And so if you wanted to query quickly what the sum of the entire list is, you can do that in what is essentially constant time, because you just need to look at the top of the list. That's exactly what we're going to be doing, because that's going to be super quick. Let's dive into our implementation here. Our example zoo had 20 total zoos to consider. In order to implement our segmentation tree, we're going to be doing that number, except we're going to add 1. So there's 2 things going on here. We have our zoos, which we want to keep one base indexing because it's really easy to just have the index be the zoo number itself, because we're going to be dealing with source zoos and destination zoos. We just want to have the number be the thing in the list itself. So we're going to be using one base indexing for that reason. And then separate from that is the segmentation tree itself. We also want to have one base indexing because the math works out for the parent-child relationships. So it's really nice to have that as well. So we're going to be having like 1 extra here and there. We are going to be creating 21 elements for our zoo list. And then for our segmentation tree, we're going to be creating twice that number, in this case 42. And it will be in this kind of structure here. We have the 0, which we don't care about. It's just not going to be used. We're going to have 1, which is the root, 2, 3, which is those children, and the children, and you can see how it's kind of like the structure here. We're only creating 42 elements. It doesn't actually fill out the entire bottom row here of the segmentation tree. That is on purpose. It is more efficient that way. This is the minimum number we need to work with. So here I'm going to actually arrange everything into tree structure, even though we know that it's a flat list. What I'm going to do is take that numbering here and I'm going to highlight which nodes represent which zoo. This thing looks so weird, right? So what we're going to be doing is we're going to be assigning and having this leaf node represents a single value within our original zoo list. Because we're doing one base indexing, this 0 zoo really isn't a real zoo, but that's what it represents, right? So the number 21 should ring a bell because that's actually the size of our original list. The zoo list is 20, but again, we're adding +1 to make it one base indexing, literally represents the length of our input list, which was what we're building our segmentation tree off of. That 21 is the start of our leaf nodes. So in this case, that represents zoo number 0. At 22, that represents zoo 1 and 2 and 3. And it keeps going. We start wrapping around and we go to 32 over here, and 32 represents zoo 11, all the way up to 41, which represents zoo 20. And the parents represent that range. You'll notice that there's a little weirdness here where like node number 5, right? Like what's going on with that? What does it represent? It actually doesn't represent anything. It's an empty or blank node. We're eking out efficiency here. And so we're creating some unused space in order to avoid using a lot more extra space using the other implementation. And I'll kind of showcase that. Here's a question. Why do it this way? This seems extra complicated. I need to optimize as much as possible. This allows us to actually implement an iterative method. I previously was using a recursive method that had too many function calls. It was taking way too long. Fewer function calls for our updates within the segmentation tree was crucial for the runtime. And the reason why it's implemented this way is because it's extremely useful for us to be able to line up and map where the zoo is represented within the segmentation tree. If I want to look at zoo number 1 and update that, zoo number 1, that corresponds to node number 22, because I just add 1, the zoo number, plus 21. And remember, 21 is just the size of the list, the original list. I want to showcase a little bit of an inefficient solution, which I saw before. Some people were doing it this way. Having that mapping is probably more intuitive to just have a whole row dedicated to your list. To enforce that, some implementations include just covering the max being some power of 2, because all things are power of 2 for this tree, right? To cover 21 elements, which is our number, then we need to have 32 nodes, because 16 can't cover that many, right? So we would implement something like this, the full tree, where the bottom row represents 1-for-1 our input list. This is easier to think about, right? Like, oh, I just go to the bottom row and just start incrementing from there. And I have my 20 that are represented, and that's super easy. As you can probably see, there's a lot of dead space over here. This stuff is infrastructure that you built out that is not being used and will never be used. Those are dead nodes. Dead nodes that are taking up space that you spent time creating. That's what we're avoiding. So let's look at what that is. And it does have some dead nodes. So don't get me wrong. It's not entirely the most efficient thing, but it's still better than the other one. And so with this implementation, we have some dead nodes here. So these are the ones that are covered black. What's interesting is that the root node is dead. So it's like, how does this make sense? How this is actually a bunch of mini segmentation trees that are grouped together in one big segmentation tree. If you actually break them up, you'll notice that this doesn't go anywhere, right? So it's just like one thing, very small. This is its own little segmentation tree, node with number 3 here, that represents a larger range, node 4 as a parent, and then this smaller one here, node 20. And that is what I'm showcasing here. I'm kind of like rearranging things a little bit. We actually do have multiple segmentation trees all jumbled into one larger segmentation tree. I've removed the dead nodes because they're not really doing anything. So we can see that we actually have the full range represented here. The relationship between the child and the parent is just math. To get from parent to child, you just multiply the parent by 2. So node 3 times 2, you get 6. That's the left child. To get the right child, you just add 1 on top of that. I'm showcasing it as like a tree structure here, but within the list, because it's a flat list. Index 3 is what I'm talking about with this. Node 3 is index 3 within that segmentation tree list. How do you get to a parent? Floor division by 2. So if you take 6 divided by 2, you get 3, obviously. If you take 7, if you're doing floor division, you're still getting 3. That is how you get from child to parent, parent to child, all math. And what's really useful, and I'll showcase this a little bit later when I talk about optimization, this is all possible using bit manipulation. So if you want to really be super efficient, all this math is just moving your bits over one or to the left or to the right, essentially. As an exercise here, I want to kind of showcase adding a +1 update over a range. Let's think about what nodes need to be updated here. As an example, say we want to update the range between zoo 1 and 12, and it's always going to be 1 at the left. So we need to add 1 to all values within this range here. So notice I have index 1 here and index 12 here. Do we need to update all the leaves? No, we don't need to do that because we're dealing with aggregates. The parents that represent that range, they're the ones that need to be updated. So which nodes, when combined, completely cover the range between 1 and 12? Node 11, node 3, and node 16. 11 represents the range between 1 and 2. 3 represents between 3 and 10. And 16 represents 11 and 12. So these 3 nodes are the ones we need to update with +1. How do we go from the input, which will be update range 1 and 12, how do we get from that point to actually targeting segmentation tree nodes 11, 3, and 16? We're going to be working with the exclusive property for the right value. We're going to be working with that number because of how the math works. I'm going to say we're going to be doing an update between 1 inclusive and 13 exclusive. First, let's convert those range values. When I say 1 and 13, that represents the zoos, but we need to talk about the segmentation tree nodes. We just add 21 to them because that's the size of our list. For the left value, we're going to have 22. For the right value, we're going to have 34. These values, so they have 2 different responsibilities, so keep that in mind. The left value, which is inclusive, is going to be climbing up and to the right, and it's trying to stay within the range to handle the parent node updates. Okay, so it needs to be within the range 1 and 13. The right number, however, is climbing up and to the left. However, it's trying to stay just outside the range. It's not trying to be within the 1 to 12 range. Okay, it's trying to stay just outside of that, which is why it's 13. Or I guess if you're referring to the segmentation node, it's 34. We start with 2 cursors, the left here and the right over here, positioned at 22 and 34 respectively. For the left side, we're saying the current index is 22. We are currently the left child And we know that because it's an even number. We can just tell just from the number which side it's on. And the side actually does matter. If it's a left child, we can say we don't need to update the current node 22 because the parent is within the range. It's not going to update itself. It's going to prefer the parent. We're going to wait to move to the parent and do the update there. We move to the parent just by doing floor division of 2. We know 11 is where we're going to move. The right hand side says we are at 34. We again know we're the left child of the parent. We're okay not updating this with +1 because we're still on the outside here. All we need to do is again go to the parent and we do floor division of 2 to get to 17. We keep going until these left and right basically cross. And this is how it's iterative. The left is now at 11. The right is now at 17. We're at 11. We know that it's a right child. And I'm not showing this dead node, which is number 5, but we know that it knows it's the right child because of it being an odd number. And the conclusion here is that we do want to update the current node with +1. We're tagging this as a node to update. So that's why it's a little blue here. We will do the +1 addition here because the parent is not contained within the range. And by the parent, I mean this dead node number 5. So we'll make that update, but then where do we go? We actually don't want to go to the parent because we know the parent is not within range. We want to go to the parent's right sibling. We don't want to go to the 5. We want to go to the 6. So how do we do that? One easy way of doing it is that we take the current index and we just add 1 to it. So we're basically moving over here, and then we take that parent. We do floor division by 2 to get to 6. So we'll be moving to node 6 after this. The right side, we move to 17. We know it's the right child because it's an odd number. We need to move to the left sibling, which is 16. Just -1 basically. We want to update that. And the reason why we do that is because there is a left sibling. The right value is supposed to be outside of the range. We know that when we are on the right side, that the left child is within range. It must be in need of updating. So we will actually move to the left child. So we do -1, you do the update, and then you go to your parent, a parent that has like a mix being within range and out of range. It has partial coverage. We will do the +1 update on node 16, and then we will move to 8 as the parent. Left is now at node 6, and right is at node 8. 6 is the left child of the parent. It is within range because the left child. We'll just move to the parent at that point. So we'll be moving from 6 to 3. On the right hand side, we are on the left of the parent. Basically, when you're on the right value, if you're a left child, then you can rest comfortable knowing that you're outside of the range because there's nothing else to the left of you. That's the idea. And there's no need to update this. We can just go to its parent. So we go from 8 to 4. So the left side is now at node 3 and the right side is at node 4. At node 3, we know we are a right child because we're odd. I'm not showing the dead node, which is node 1. When you're a right child, we know that's the time that we want to update. We do the +1 update here. On the right, we are a left child. We know that because we're even. Node 2 is not being shown here, but that's a dead node. There's no need to update. Remember how parent 8 had kind of like a partial coverage of something that's in range and something that's not? When you have that partial, this is like an impure parent. That sounds so weird. It's not purely within the range. The right-hand side is still outside of the range, essentially. And so there's no need to update that. We go to the parent, which is 2. And at that point, the left and right-hand sides are both at the same value 2, and we can stop iteration at that point. You can see what we've targeted here, 11, 3, and 16, and we're able to iterate them in this way because we have essentially a while loop. While these two values are not met, keep iterating, and that's how we'll be doing it. This is not a recursive call, it is an iterative implementation. What is this algorithm we're following for the +1 updates? First, we need to ensure that the input range has an inclusive left side and an exclusive right side. What we want to do is add the length of the zoo list because we're basically converting from the zoo number to the segmentation node number. While the left index is less than the right index, we can keep iterating in this way. For the left index, if it is odd, meaning it's a right child, then we want to make an update. And we'll be moving after that update to the parent's sibling, the right sibling. Otherwise, you just move to the parent. And for the right index, if it's an odd, meaning it's a right child, then we will move to the left sibling, update it, and we want to move to that parent as well. Otherwise, you just keep moving to the parent. So you'll see here that otherwise move to the parent is kind of like the standard. You're basically always like going up 1. That seems complicated enough, I'm sure, right? The issue is we've only handled 1/2 of the problem. The additions, the +1 additions, which we're able to handle within our sort of multi-segmentation tree. What we haven't talked about are the max values, because we're doing this thing where we update +1 across a range, but we also have this idea of actually having the max value and querying for the current max value. The way we're going to handle this is by having a whole second segmentation tree that is dedicated for max values. And what's nice is that they're basically like mirrored on top of each other. It's helpful to have them kind of have the exact same shape. And you'll notice here I'm including the quote unquote dead nodes, and I'll explain why in a second. We're going to duplicate the exact same tree structure. And instead of using and storing the +1 aggregations, we're going to store the max values. This means that each parent will store the max value found within its range. Here's something to consider. We can actually use the dead nodes here for the max value querying. We mainly just care about getting the max value for the entire tree, because every time we're looking at the next zoo, we've only updated everything up to that point. So we don't need to really look between this range between 1 and 12. We don't care, right? It doesn't really matter because we are currently at whatever the zoo number is. We can just query the whole thing. And remember what this root represents. That represents the whole thing. If you're using aggregates, then this is just the max value of all of these sort of mini or sub segmentation trees. So we can actually use these dead nodes to just gather and put all the way at the top, the root node here, what the max value is for the entire tree. And we'll just query that, and it's super quick. One minor thing to keep in mind is that whenever we do the +1 additions, we still need to transfer those into the max segmentation tree. I'm changing up how I'm showcasing my segmentation tree right now. So what's in the box now is going to actually be the value for the additions and the maxes. I am showcasing essentially two segmentation trees, one which is the additions and also the maxes, but when we actually implement it, we're going to have two separate trees, entirely separate. As an example, I'm going to switch things up a little bit. So these are not the same animals as before. This is a new set of cats and dogs. It doesn't really matter. I'm just trying to showcase like following the process here. We're going to be creating our source zoos by destination zoo list, and that's basically what I'm doing here. So I'm just taking this, popping it all into this list, and we're essentially using counting sort to fill everything in. So our first animal is a cat at zoo 7, which was picked up at zoo 5. So we'll need to update and tell this cat segmentation tree, hey, do +1 additions to the animals at and before zoo number 5. So we have basically like 4 trees I'm representing here, a cat tree and a dog tree. And within those, we have cat addition segmentation tree and the cat max segmentation tree, as well as a dog addition tree and a dog max tree. We're only updating the cat one right now because we have one cat being delivered, so that's the one we're going to focus on. We are trying to add 1 to all values within this range between 1 and 5. We are actually going to be talking about 6 exclusive here. First, let's convert the left and right ranges here. We're going to talk about left being 1 plus 21 or 22. The left side is always the same because it's always starting at 1. The right side is going to be 6 plus 21, which is 27. And again, we're using 6 and not 5 because we're talking about 6 exclusive. Here we're starting at node 22. There is no need to update because it is on the left hand side. We want to update the parent because the parent must be within range. On the right hand side, 27, we are the right child, so we actually know that our left sibling must be within range, and so it needs to be updated. And so we will move to the left sibling, update it with +1, and that's what I'm doing here. So you see how there's a 1/0. That means the 1 before the slash is the additions. Then we'll move to the parent. So now we're going to be moving. Our left has moved up to 11. Our right has moved up to 13. So the left is a right child. Again, it's the right child of 5. So we know that the right child is something that needs to be updated because its parent will not be within range. And so we do the +1 addition at this point. So you see here, I have a 1/0. That means it's an addition. We will then move to the parent's sibling. This right sibling is 6. That's what I'm talking about. On the right hand side, we're at node 13. 13 is a right child. We know that the left sibling must be within range. It needs to be updated. Add +1 to that. So it's 1/0 there. Then we'll move to that parent, which is 6. Because we're now at 6, both are crossing, and then we can stop iterating at that point. So here's what has happened. We've updated 11, 12, and node 26 here. Does this make sense how we updated it? Node 11 represents the range between zoos 1 and 2. 12 represents 3 and 4. Node 26 represents just 5. So we've updated the range between 1 and 5. The ones that were necessary to update all have +1 additions. Now, we haven't talked about the maxes at this point. Here's how we're going to handle those. We need to bubble up those additions. So we only updated 3, 11, 12, and 26. Because those were the only ones that got updated, we will then take those nodes and we'll bubble up those values into the max list. Here I have a max seg tree update list, which is just keeping track of what has been updated. So the first node is node 11. So we're going to start with that. We're going to move to the parent, find its children, which is actually 10 and 11. And you're basically going to calculate the max value of the left child, which is its additions plus any current maxes that it has. And then we're going to go to the right child and calculate its max, which is again the additions plus whatever max values it has. We get the max value here of 1. So you see there's an update here of 0\1. The \1 is the max value. We're going to take this and go to its parent and then its parent and then keep going basically. So we repeat the process until we reach the root. Then we go to 12. It was updated. We go to do the same thing there. It got up to the root, but the root didn't actually change. The last one is node 26, and we can just stop almost immediately because 13's parent is 6, and then it's already at max value of 1, so there's no update there. So once we know that a parent will not be updated with a different value, then we can just stop there because it's not going to be, you're not going to get a more max value than that. So at this point, we can now say that the cat segmentation tree has been updated. We're done with zoo number 7. Now we can ask, what is the max number of animals that could be delivered between zoo 1 and 7? And all we have to do is look at the top. There's 1 for the cat tree and 0 for the dog tree. So we have 0 and 1. Of course, we want to go with 1. And we go to our zoo max counts and we update that and say, at 7, we have a 1. We need to update our dog segmentation tree with that information. It doesn't know about the current max, so we need to tell it that. And the way we do that is to update it at zoo 7. We're going to go into our dog tree and we're going to go to zoo 7. We're going to go to that index, which we can find very easily. It's just 7 plus 21. We update it and say max is 1 now. That's the best that we have so far at zoo 7. And then we just bubble that up. We now can see here both trees, bam and bam, they now are aware of the max value so far. Okay, so at zoo 8, we see 3 dogs, and they all started at 2, 4, and 5. We will be updating our dog tree with +1 additions, and again, between 1 and 3, exclusive, 1 and 5, and 1 and 6. I'm gonna go a little bit quicker here, but essentially, to handle the 1 to 3 exclusive range, we're gonna be updating node 11. For the 1 to 5, we need to update 11 and 12. And so you see now it's gone up to 2 for node 11. And for the additions between 1 and 6, again, 6 exclusive, we're going to do +1 to 11. So it's at 3, 12, which is at 2 now. Node 26, which is just the 5th zoo, it is going to be a +1 there. We did all these changes, but we've kind of did updates to the same node multiple times. For example, node 11. So what we care about is really like the unique nodes that were updated. And so if we keep a list of the unique nodes, we will have 11, 12, and 26 that need to be updated. For node 11, we go to the parent. It actually has 3 additions on node 11. So the parent says, okay, the max is 3. That bubbles up to 2 and also the root of 1. Then we will do 12 as well. 12 gets 2. It bubbles up to 6, 3. It doesn't go to 1 because 3 is already bigger, so you would actually stop short here because you don't need you can't update that with a bigger value. Node 26, we basically just stop at node 13 because once you get there, you have an update of 1 max, but the max at 6 is already 2, so it's already larger. And we're now done with zoo number 8. This should be an 8. And now we get to ask, what is the max number of animals that could be delivered between 1 and zoo 8, the current zoo? The cat tree, which has been unchanged at this point, still says 1, and the dog tree now says 3. And so we will say, okay, 3 is the max. We go to our zoo max count list, say 3 at 8, and then we will need to communicate that information now to the cat tree, which needs to be updated. Go to node 29. 8 plus 21, and your max is now 3. Bubble that up. Now the root has 3 as its max. We can move on to the next zoo, which is zoo 10, and now we see that we actually have 2 different animals being delivered, a cat and a dog. This one started at 9 and this one started at 3, so we need to kind of update both trees. On the cat side, we're going to be updating between 1 and 10 exclusive, and so those nodes are 11, 6, 14, and 30. I will just handle all these updates to the max as well. Eventually we'll get a 4 at the top of that. Pause if you need to actually see which nodes are being updated, but that is how that works. For the dog, we're going to be doing a 1 to 4 exclusive update, which is going to be node 11 and node 24. We are then going to bubble those changes up, and again we actually get a 4 for that as well. Do you want to showcase one thing here? We can start seeing how we can maybe optimize here, and that's what we're doing for the cat. When we did the update here at node 14, this is where we get to see the interplay between a truck that was dropping off a dog, which is now empty, and now picking up at a cat. At node 14, this 3, if you remember, this 3 came from the dogs who were all dropped off. There were 3 of them. That was a max at zoo 8. That was a previous max. And because we're doing this +1 addition across the range, it is now being updated with one more, an animal that could be picked up after zoo 8, in this case zoo 9. This 4 represents 3 dogs and then a cat being dropped off. Okay, so with both trees updated, we ask what's the max between 1 and 10, the current zoo. We get 4 for both, and we will go to our zoo max count, say, well, 10 is a 4. And we don't need to update these because both zoos are aware of the max of 4. So we just kind of leave them as is. We don't need to update anything. And we're going to move on to our last zoo, which is zoo 20. There are 2 cats, one started at 2 and one at 16. For the zoo starting at 1, we just update node 11 essentially. And then we will again do an update, but this time between 1 and 17 exclusive. We're going to be updating 11, 3, 8, and 18. When we do that, we will then need to bubble those up into the max list, and eventually we get a 5 for the cat tree. Again, we can see some interplay here on node 3. We can see that this, which was interesting enough, was 3 dogs and a cat. Here we're now adding 1 more because we're picking up a cat at zoo 16. We can now add another cat onto that. And so we have 3 dogs and 2 cats, essentially. That's what that 5 represents. All right, we are done with the updates. We ask, what's the best? We see the cat says 5. We will go to zoo max counts and update that at 20 to be 5. Our dog list will need to be updated per usual at zoo 20 or node 41. We add 5 as the max, and we bubble that 5 all the way up to the root. So now it is aware. We are now done looping through all the zoos, and we have our zoo max count list, which is here. We then convert that to our answer list. So I know that took a long time. It was a very long-winded. It took me basically 2 years to figure this out. So maybe I'm like overdoing it. I think it's really helpful to actually see each step how it's working. All right, folks, we are here in Python land. I'm on HackerRank here. This is the Python 3 language. First off, I want to establish this zoo count. We're going to be using that a lot because of the one-base indexing. The cat sources by destination zoo list is being created here, is essentially a list of lists, cats and dogs being created for that. Okay, so we're going to go through each animal and we're going to properly put them in the right place. For I in range n animals, and we're going to grab the source zoo and destination zoo. Those are both numbers. So if you have a source zoo that happens after the destination zoo, we ignore those animals. So here, if the animal is of type cat or elephant, we're going to just lump them all together, basically. I'm just going to call them all cats, essentially. Put all the cats in the cat sources by dest zoo list of lists, and we're going to put it at the specific destination zoo it's getting dropped off at, and we're going to append the source zoo to the list at that point, and everything else is a dog, and we do the same thing for the dogs. We're going to establish our segmentation trees for cats and dogs. I'm going to go into those implementations in a second, but I want to kind of get through the logic first. We're going to keep our zoo max count list. If you remember the visual, if I go back a second, it's the one that is essentially like one step away from our answer. So here's our main loop. We're going to go through each zoo index. We're going to grab the sources for the cats and the sources for the dogs. And if there are none for either one, we could just skip this particular iteration because there's nothing to do. If there are cat sources, then we will go to our cat segmentation tree and we will do the +1 additions by sources. So here I'm just going to pop in the whole list and the segmentation tree will handle it. And for the dogs, we do the +1 additions for them as well. So at this point, both segmentation trees have their +1 additions done. So we can now ask, what's the max value? We will grab the best one. So we get the max of the maxes, and then we will then assign that within our zoo max count list. Now that we're done with that, we have the best max that we have. We need to update the appropriate segmentation tree. If both values are the same, then they both are aware of the max and we don't need to do anything. So here again, we're continuing because there's nothing to update. However, if the cat value was the max, then that means the dog tree needs to be aware of it. We're going to update the dog tree with the best max at that zoo, which is the current zoo. And that's doing the update, again, bubbling it up all the way to the root as well. If the cat isn't the best max value, then it must be the dog with the best max value. And therefore the cat segmentation tree needs to be updated. And we're doing the same thing for the cat tree. Now that everything's updated, we're going to be looping through this all the way to the end. And now we will have our zoo max count list completely filled out. I haven't talked about this segmentation tree implementation, so I'm going to go up to where I define my segmentation tree all the way up here. So here's our segmentation tree. It gets initialized with a zoo count. I'm storing that internally, and then I'm creating essentially 2 trees. I'm taking the zoo count times 2, and then I'm just making a bunch of 0. So it's just 2 trees that are exactly the same shape. I'm going to keep internally this idea of a first zoo node because we're doing one-base indexing. I want to know what the zoo number 1 is because we're using that for basically everything. All the +1 updates is like zoo number 1 is like the starting point. Zoo count +1. Here I have a simple method to get the max. It just takes the top of the max tree, which is the root, and the root again is 1, not 0, because 0 is not being used. Here we have a method called make +1 additions by sources. It's going to take a list of sources and it's going to loop through them and then call another method. I mentioned about having all the unique nodes that were updated. That is what's going to get handled here. I'm creating a set. So within that method, you're going to be updating a node. And then when you do, you add it to the unique updated node set. And then after all that, you bubble up the maxes. So we'll see both of those. So first this, and then we'll talk about this one. So this method is right here. It takes a single source. And remember, the single source is currently the actual zoo index. So we need to actually get the left and right segmentation node indexes. So that's what we're doing here. The first one, the left side, is just going to be our first zoo node, which is zoo number 1. And our right is going to be the source zoo plus that first zoo node. This is supposed to be exclusive. So the fact that we're adding the first zoo node means that we're basically adding one on top of it already. So we're essentially in the exclusive form already. So the left and right are being handled that way. While the left and right are left is less than right, then we check, oh, is the left an odd number? If it's odd, we know we need to do the update. If it's odd, we do the update at that actual index. So this is on the additions tree. And then we add that to our set. And then we increment our left by +1. And remember, when we do the update for the left-hand side, we do +1 because we're going to then get the parent of that. And we're always getting the parent essentially. So that's why at the bottom, just for efficiency, we're just doing that one time. If this is not the case, then the left side will just get its parent. If the right side is odd, then we know we need to -1 to get to the sibling, the left sibling. So we do the -1 here. So notice that we are doing this decrement first before we do our update. Then we update the additions on the right with a +1. And then we did the update. So we add that to our unique set. As always, we will get the parent of the right either way. So eventually we get to a point where the left and right cross, and then this will stop. So that's for each source. Then we will take our unique nodes in our set and we will bubble up from those. So let's check out where that is. So here we're going to say for each node, we're going to get its parent. And while the parent node is not 0, essentially, get the left child and the right child. That's the index. So you need to add the additions plus the maxes to get the max for the left child. And then once you do, you will then get the max between both. That would be the new max. However, we want to do our stop early logic. So this is what that is. If the new max is actually not going to be better than the current one, then we just break because we don't need to do any more updates. However, if it is, then we get past that and we will set the parent node maxes to the new max, and then we will get its parent. And then we'll keep doing that until parent is 0, essentially. That's all that the +1 additions is doing. The last method to talk about is this one called update best max at zoo index. We will be getting a best max and we'll be getting a zoo index, and we are going to basically update that directly on that zoo/node, and then we're going to bubble up from there. Remember that we actually are getting the value and it is the actual zoo that we want to update. So we're not going to be doing this whole like exclusive thing. We're going to just take the zoo index plus whatever the size of the list is, which is the zoo count. So we're going to say zoo count plus the index. So we're converting it to like an actual segmentation tree node index value, and we're going to be updating the maxes. So we're only handling maxes for this. So we take the max and we're going to set it at that node, and then we're going to bubble up from there. So we're going to take the node and we're going to get the parent of that. And then while we have a parent node, we're going to get the left child index, right child index. We're only dealing with the maxes. That's all we're going to handle here, left and right. We're going to get the best max so far. And again, we stop early if we need to, but if we get past that, then we set the parent's node as the new max, and then we grab the next parent, the parent's parent, and we keep doing that until we get to 0, essentially, and it will stop there. And that is what update best max add zoo index is doing. Now we can just go through the logic of getting the answer. Okay, so here we're establishing our animals list. This is basically a bunch of -1s as a list, and it is n animals long. We're going to have a variable called animal count set to 0. This is essentially also our index within our answer list. So keep that in mind that this is serving kind of two purposes. And then we're just looping through our zoos. Once we're in the loop, we're going to say, okay, while the animal count is less than this value, which is the zoo max count at that zoo index, then we want to keep going through our answer list, making sure that that zoo is the one that is represented there. And then we increment our animal count by 1. And we keep doing that until we get to a point where the animal count is greater than the value at that point. And then we can now pop up here and go to the next zoo. The one thing to keep in mind is that this is not an equals because we are starting at 0. We're basically kind of like doing a -1 to this because we're using this as the count, but also as the index. So this should work. So let's run this. All right, so that looks like it passed. Let's submit some code. So they made some changes to this. Hey, look at that. It didn't pass. So I'll showcase this here. So it says the time limit exceeded. Okay. This is the same code. I'm just going to hit submit one more time. Let's see what happens. Look at that. Now test 21, 20, 22. They didn't exceed before. I'm just going to have to hit submit again. And let's see what happens. Okay, so I'm going to stop here for a second. This clearly shows that there's some inconsistency happening here. So what's going on with this time limit exceeded thing? So if you click on this environment page, you can see here by the coding and database, environment, documentation, coding and database. And you can see all the different languages and whatnot. We're going to go down to Python. So it's basically saying that you only have 10 seconds to pass your test within that test suite. This test case 21 actually has like 7 or so tests, individual tests within it. So when you see this here, this is the code that is being used sort of like without your knowledge. It's basically taking this input as a number of cases. So there may be multiple cases. There are going to be multiple cases for those harder ones. And so for each case, it's taking the input and then dumping it into your solution. There's a lot going on here. That 10 seconds is actually really hard to hit with this fairly efficient code that I could not for the life of me get to work. So there are 2 gripes I have. Temporary rant here, folks. Okay, my first rant is this editorial was not very well written. There's something here that just really got on my nerves here. I was just trying to figure out the dynamic programming part, which is like only 30% of the tests will pass with this. So this dynamic programming was really important for me to just understand the problem. Doesn't make a whole lot of sense what's going on with this. So this person doesn't explain it very well. But then there's this sentence right here. The people who go to the editorial, and I'm talking about people who are struggling like myself. This is where the help is supposed to be. The discussion was horrible. You look at the discussions, it's horrible. It's a bunch of like spam. No one, it's not good. And so you go to the editorial for help. And this is where the answer is supposed to be. Here's what you're supposed to get the explanation. After all of this stuff, they say, oh, it's the worst time complexity is this. To find the minimum number of zoos visited using this dynamic programming, you just have to tweak it such that you are choosing the animals from right to left. I am sure you can figure that out. That's what I came here for. I came here for you to help me because I'm having trouble figuring out myself. Do not put this, okay? If you're going to provide help, provide help. Don't tell people to just figure it out themselves. That's just, just grinds my gears. Okay, that's my rant on that. The second is with the Python implementation. So I looked at this author's code, which is written in C. Couldn't really make sense of it, but I got an understanding what was happening. They were sorting, and that's what they say. They explain their solution. That's what they're doing. They sort their animals, and then they process it in a similar fashion to how we're doing our segmentation tree. I could not get it to work. I then went over to, and I'll show you what I'm doing here. If you look at the leaderboard and you look for Python, I was looking at their solutions. I tried going to PyPy, which is a Python derivative. You can just copy and paste the code. It's the same thing. It's Python. They're passing solutions for PyPy. And so the solutions that you have for this, again, not very well explained, but I can't really fault them for this. You copy and paste it into Python. I'm talking about Python 3. You just do that. It's not going to work. Through blood, sweat, and tears, I do have a passing solution. However, it does require going hard on being as efficient as possible. Anything that you can eke out, you need to do to get it working in Python. You can hit submit all you want. I will say that if you hit it enough times, you might get timed out for one. I didn't realize that was a thing. I learned that the first time. You won't have consistency if you use my final solution, which is like super minified, which looks like this, right? Cannot read this for anything, right? But if I hit submit, look at that. I can get the test to consistently pass with that. How did I get there? That is the next section, okay? So if you just need to understand how it worked and this previous solution makes sense to you, great. You can use that. You might have to hit submit a bunch of times. Eventually it'll work maybe. But if you want to talk about like getting it bleeding edge efficiency, that's what I'm talking about next. All right, so the first small bit of efficiency that we can do is with bit manipulation. It is really just shifting the bits for a number. For example, when we have this zoo count times 2, instead of doing this with math, we can just shift the bits over by 1 because that is essentially multiplying by 2. And that's much quicker because that's essentially talking like machine code anyway. This math is being used a lot for like traversing the tree. So it would be more efficient to do it that way. I'm not going to be talking about bit manipulation and explaining how that works. There's plenty of other resources for that. I suggest, looking into that for a little bit. We can say zoo count and we shift the bit over by 1. And that is the same thing. That's exactly what we're going to do. We're going to replace that particular code with that. And we're going to do the same thing. We're going to kind of search through to see where else do we have bit manipulation stuff that we can do. One thing I see here also is checking for odd or even. So instead of doing this modulus 2 and then checking for equivalency to 1, we can actually just see if the 1 bit is there. And so that is how you would check to see if the number is odd. Just say and 1. So we do the same thing here, and that replaces it. And remember, this is going to be a method we're calling a lot. So the fact that we can eke out that efficiency is actually pretty significant. So here we're doing floor division. Okay, so we're not going to be doing floor division anymore because we can just shift the bits over by 1, the other direction, to the right by 1. And in fact, we can do a shorthand, shift the bits to the right by 1 like that. And that is actually saying the exact same thing. Pretty cool, right? So very efficient. Here we have a parent node. So what's interesting is that this node can just be reused. So I'm gonna reuse it and do the same thing. We no longer have parent node. We just have node. So let's just call this node, parent node, parent node, parent node. Okay. Multiplication by 2. So we know we can just do, again, bit manipulation here. You shift it by 1. That's basically multiplying by 2. And we do here, we can do the same thing here where we, instead of dividing, we can just shift the bits by 1 to the right. And for our update best max, we can do essentially the same thing. So I'm gonna actually rename this symbol to just node. So that changes it everywhere else. Once we're done doing this update, the node, we can just kind of reuse it and we can divide by 2. So that's shifting it over by 1. And that is that. And we're doing the same thing for the parent down here. So I'm just getting the parent node here. Node times 2, we can just shift it left by 1. And that is that. And I think that's all that we do. That's all the math stuff, right? Okay, yeah, I think that's it. Let's run the code, see if it still works. Okay, it still runs there. Let's submit. That's so crazy that like it's so inconsistent. It's so mind-numbingly annoying. Anyway, so that's our first efficiency boost. Our next change is calculating the max, which oddly is inefficient. You have to keep in mind that under the hood it's using C and things like that, so it's actually using lower level language to do this. However, it is assuming that you're also throwing in list and other iterables, and so there's actually a bit of overhead with this function. This default Python function is actually not as efficient as just doing really simple check for the max. So here I'm going to say left child if left child is greater than the right child, else right child. So this is actually better and faster than just using the max default function. Let's see the next place that we use max. Update best max zoo at index. I'm going to do the same thing here. And that's that. And I believe there might be one more. Oh, yeah, right there. So this is within our main loop. So this is getting called every single time. So we definitely want to be efficient here. So we can do the same thing. All right, let's run the code, see if it works. And let's submit some code. Maybe we'll pass this time. Well, hey, look at that. It did pass. I will say that it may have passed this time, but it's not consistent. Here's the thing. This stuff is working better than it was when I was working on it. And I did do something here. I did hit suggest edits before I actually came up with my solution. Here is the email I got from them. They said, hey, we have received the following suggestion. And I told them, Python 3 timing seems impossible. Please consider bumping the timing for Python 3. And they said, we will consider changing the problem. And that was on October 7th, 2022. It seems like they may have changed it or bumped it up or something, because I will say that me hitting submit on this code right now as is would never have come close to passing. It wouldn't have even made a dent, honestly. The fact that it's passing all of them, I think, shows that they did do those edits. So yay. All right, the next thing that helped greatly was essentially removing this class. So this was a big change. We're going to take all this stuff and make them functions. And that means that all these trees that we're talking about, the additions and the maxes, we'll need to handle them as variables internally, which is fine. It's not that hard to do. It's just kind of like rearranging things. Okay, so I won't bore you with all the details here, but I basically took the segmentation tree class, removed it, and implemented all of those methods as functions. So I had to remove the self-reference because that's not a thing in functions. And I do have to pass in the trees that we're talking about for that particular method. For a bubble up node, it's kind of like the same thing. We're having to pass in the additions and the maxes. For update best, we have to just take the maxes because that's all we care about for that. I will say one small change here is us handling the segmentation trees within our main function, our minimum zoo numbers function. Here we're establishing those segmentation trees. Notice here that I'm actually copying the list. So I'm establishing the list once here as cat additions, and then I'm essentially copying. And this method for copying was actually the fastest way of doing it. It's faster to copy it than to create it anew. That is why that's happening. So another change we're doing here is within our main loop. Previously, we had a method here for handling all of the sources. I felt like we didn't need to do another method just for that. I'm just going to create our set for unique nodes. At this point, I'm going to loop through each source within our cat sources, and then I'm going to call the method, or I should say function, add one up to source, and I'm providing the variables. And once you get through all those sources, you will have a collection of uniquely updated nodes. You're going to call the function to bubble up as expected. So that's like kind of the cat getting handled. We will do the same thing with the dogs, with dog related basically. Previously, we had a method on the class to get the max. We don't really need that because it's super easy, right? It's just like grabbing the root node. I'm not calling any method or function. It's just getting it directly off of the tree. We have access to it. It's readily available. All right, so with those changes in mind, let's run the code, see if it still works. Hopefully it does. Yes, it does. Okay, so let's submit some code. And let's see if this one passes this time. Now, mind you, now we've just removed the whole class, so this should be even more efficient than the last one. So it might pass. Hey, this one passed all of them. Yeah, they definitely changed the timing because the requirement before would not have passed this. Because I tested, like this was literally 2 weeks ago. It still wouldn't have passed. Even it wouldn't have come close to passing on most of those last tests. Like the last, I think 6 or 7 tests. This was maybe passing 2 of those like last 6. One more efficiency we can do is with our initial list, because we can be a little clever here. So what I'm going to do here is I'm going to actually remove this and just have a single sources by destination zoo. The idea is when we have, let's say cats, we'll keep it as a positive number, but when we have a dog, we will use a negative number. And then when we actually loop through it, we'll handle one versus the other. I can also make this a little bit more efficient because I can take this and put it within this statement here. If it's a cat or elephant, you get the source zoo, else you get the negative source zoo. And therefore, we don't need this statement here. So now our sources by des zoo will have both a collection of cats and dogs, potentially. The dogs are negative, the cats are going to be positive. We'll have to change this up a little bit. And then we can just say, well, if not sources, we can skip. But now we have to kind of do a little logic here. We can keep the sets themselves because those are going to be unique to each animal. If that source, the individual source, is greater than 0, then we know it's a cat. So we can just do the cat thing. Else, we know it's a dog, and we'll do the dog thing. So we're just doing the additions here. We're not doing the bubble up dates yet because that is a separate thing. So this basically handles, for each source, we're going to update the correct animal additions. And then once we're done with that, we will have a collection of unique updates for cats and dogs. Then we will bubble them up accordingly. All right, I forgot one last thing, which is the fact that our source for the dogs is negative. So we actually need to convert that back to a positive. Once we do that, let us run some code. Excellent. Let's submit some code. All right, well, it happened to pass. Okay, so it's definitely passing consistently at this point. So honestly, if you wanted to stop being efficient, you could do that here. But there's actually a significant amount of more efficiency that I had to eke out just to pass the test from like 2 weeks ago. I want to showcase what I had to deal with. This thing was insane for me to deal with. So I'm documenting my process. That's all I'm doing right at this point. So within our main loop, you'll see that there's a lot of, this stuff going on here. Basically, I found that by taking this and putting all this stuff within its own function. I'm going to cut it out right now. I'm going to call it sub because I'm like substituting, and I'm going to just kind of paste everything. So notice that I'm defining the function within the function, within the minimum zoo function itself, because that way I have access to things like cat additions and stuff like that, the stuff that's established within the function. One thing I have to change, that we're no longer in a loop, we are in a function, so we can say return here instead of continue. And so we need to call our sub function. We need to provide it with some things. And I think the one thing that we need is the sources. So let's say that's coming in from here. So sub sources needs to be defined, and that it is. And so once we are in our main loop, and look how nice this is. Like now we can just say if sources, we call sub, and therefore we're still skipping when there's something worth processing. Okay, and that's all we're doing. That's the only real change here. So now we have our main loop, which actually looks very succinct and very like neat. Our sub function is up here. I did find that it was a pretty substantial boost in efficiency, like the runtime was quicker. This will probably pass at this point, but let's see just in case. I wouldn't be surprised if it doesn't. But every time I see this pass, I'm like bewildered because like this wasn't happening literally 2 weeks ago. So wow, it passed. Like wow, that's like amazing. I hope they took my feedback. Maybe I'm the one who made it happen. I want to think it did. I want to think it was me. I want to think that. So one thing you may realize is the max tree, this one and this one. When we're looking at it, and I'll kind of go back to my diagram. So if you're ever looking at the max side of things, the leaf nodes, which are the nodes that actually represent the zoo, the +1 updates will never touch the leaf nodes. The only time that we update a max value for the +1 additions is for the parents. We do touch the max value when we do an update. That's when we actually change the leaf node. This array, which goes from 0 to 20, for example here, is exactly like our zoo max counts. You can just use that bottom part of the tree for the max count. So that's actually what I'm going to end up doing here. So this like intermediate here is unnecessary. We're creating a list when we don't have to. I'm going to kill this and delete it. And so now we're going to use one of these. I'm just going to pick the cat maxes just to pick one. First, let's go down here. We have maxes, and here we have our zoo max list. So we're not using this. We're going to be using the zoo index, but remember that we're now dealing with the segmentation tree. So we're going to have to get the node for that. So with the node now in place, we will take that index as the node. We're not going to be using the zoo max count list. That doesn't exist anymore. We're going to be using the cat maxes. We're directly updating the max value within our cats maxes list. And so when we call our update function, which I could kind of click on here, you'll notice that we basically are redundantly doing that already. We're going into the maxes list at that node and setting the best max. So we can just do that manually within the main function and then not do it here. We can just take the node and bubble up whatever the max is at that point. We don't need to pass in the best max. So we don't need the best max anymore because we're going to handle it directly here at this point. So now we need to actually do that for this, because this is when the cat is the max. I see now that this is a little redundant because this is the same thing as up here, right? So let's remove this. So if the two values are the same, then we just return, we're done. We've updated our source of truth. If the cat is the best, then we need to tell the dog about it. And so now the dog maxes need at that node to be the, oh, actually, you don't even need that, right? Because this best max is unnecessary, because if I remove that, I just set this to the current cat max. So we've updated our source of truth. The dog max might be higher, right? So here's our logic. If the two values are the same, then we're basically done. We don't need to update anything. So we're still updating our source of truth with the right information. If the cat max is greater than the dog max, well, then it's the max value. The cat max is the max value, which means that we've updated the source of truth with the correct information anyway. And now we just need to tell the dog about it. So here we're doing that. So the dog is now aware. Otherwise, the dog had the best max and the cat tree needs to be made aware. And we would update the cat tree with the dog's max. So that's what we should do here. I guess we could just pull this down actually, because that could be before this return statement. And here, the cat maxes will now need the dog max, because the dog is actually the better one here. We need to keep our source of truth even when the dog is getting updated. I will say at the bottom here, we have our source of truth, but we're not using that anymore. We're using the cat maxes, but again, we're using the zoo index. We need to get the node, and that is the node here. So let's run the code there, and that passed, and let's submit some code. Currently, we have all this boilerplate stuff going on. We have this, input being read in, it's being parsed for us, and then that's being dumped into our function, and then the result is being written to a file, and that is our answer. That's a lot of stuff happening, and you could think maybe this is inefficient. We could just put our code here, and instead of having the result be like the result of a function, we could just like have our code right there. What's also interesting is this writing isn't necessary. Writing to a file is not required because if you just print, that gets read as the answer anyway. Okay, so we're back here. I've basically did what I said. I haven't touched any of these functions. The functions are still the same. What we have different here is this. Get the input as an int, and you're gonna go through each case, and you're gonna just basically parse out the standard input yourself. This works because I'm just dumping the entire function into this for loop, which is calling our function anyway. We don't return an answer now, we just print the answer. So let's rerun this. All right, that passes for sure. All right, there are two more things I will mention, and then I'm basically done with this freaking thing finally. We preferably do not want to use anything from the global space. It's quicker to access things that are more local. Whenever you're calling something like range, which we're using a lot, by the way, one trick you can do is just to redefine those global variables as local variables and then just use the local variable. All right, so these are the global functions that we're calling: input, range, and ints, and we just need to replace any instance of that. So I'm gonna make those changes in a second. Okay, so I just did the replacement for all those. We are running multiple tests, and what's interesting is we are creating new infrastructure every single time. But you can imagine that if we could potentially reuse some of that infrastructure between tests, we can just be more efficient that way. And sure enough, we can certainly do that, at least in 3 ways that I found. This sources by dest zoo is potentially something we could reuse between the tests. So we could just take this out and put it like up here. So I'm going to put these as like, so that's 1. But instead of the range of zoo count, which we don't have defined, we'll just use 10 to the 5th because we're told that in the problem that that's the max it could be. So we're just going to use that. We need to do some updates here. We grab it out of here. And then once we're done with it, we don't need it anymore because we're going to the next zoo, right? Here is a perfect place we can kind of like reset it. I'm going to actually use the sources list. It's an object reference. So we can just clear that list so that the next time we go to the next test, we can just reuse this sources by dest zoo. Another thing we can do is this here, these sets. This was a kind of interesting find, but we're going to move that. Again, it's a small data structure, but if you don't have to keep recreating the set and just clearing it, clearing a set is super quick. What I found interesting though is that a set is not faster for our purposes than just a dictionary. So we do need to change some things. So here we're going to take our updated and we're going to just say clear them out. Each loop we're clearing the appropriate list as well as the set that, or I should say dictionary of unique updated nodes. We do need to change where we do the dot add, however. So we have a function here that calls dot add right here when we add it to the unique. So instead of adding it, we can just reference it like a dictionary and just assign it to some value. It doesn't really matter because we're not using that value, we're using the key. So when we use this, we'll be reusing these variables because they'll be cleared at that point. So we don't need to keep recreating it. Therefore, it's more efficient. So let's run this. This was a pretty big bump in efficiency I found. So this is basically done at this point. There was one last step that I felt I needed to do just because I could, and that is to minify. Python minifier, python-minifier.com. See what it does. It basically takes all the variables and shortens it. The code works the exact same way, except now it is done in the smallest way possible. It looks like gobbledygook, right? But it has all the same stuff, right? It just uses variables that are shorter. And if I run this, I felt I needed to do this just to get it. I just tried to eke out every little efficiency I could. My goodness, this thing. Oh. Well, folks, that is it for today. Hopefully that was helpful. I don't think I'll be the last one getting the leaderboard here at 70 points on Python. But anyway, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I'll see you next time. Take care.